out.
Okay.
Thank you.
I don't understand what they were thinking when they posted the.
Okay, we'll wait till 6:35 to start the lesson. All right, I think we can probably start now. So this week we're going to be talking about complex numbers and then trig and complex numbers. So today I'm just going to cover some complex number basics, and then on Thursday, Derek will be talking about trig and complex numbers and some other applications. Let me. Okay, so yeah, so for today we're gonna first do an introduction on what complex numbers are. And then we'll do cover how to do arithmetic with complex numbers, and then we'll talk about the complex plane, and then finally complex roots. So, yeah, so this is so we'll go over the definition first. So real numbers are basically what we've been working with so far, and these are numbers that can be plotted on a number line, and they include all rational and irrational numbers. Um, So the square of a real number will always be non-negative. So that's like a property of that. However, for complex numbers, that is not necessarily true, and the square of a complex number can be um, negative. For example, I is root of -1, and we see that I squared is equal to -1, so that means that it's an imaginary number. So all real numbers are also complex. Oh, wait, okay, let me first. So complex numbers are of the form a plus bi, where a and b are real. And we say that this part a, we say that a is the real part, and then bi is the imaginary part because b has the I. And then we also know that all real numbers are complex because that's just the case where b is equal to 0, and then we just have that the number is a. And since a is real, that means it's a real number. And if we have b is not equal to 0, then we say that this number is non-real because it has an imaginary part. And if a is equal to 0, then we are just left with bi, and then we can say that this is pure imaginary because there's no real part. And now we'll go over a complex. How do I? Two people are in the waiting room. Okay, so for the people who just joined, we're going to be talking about complex numbers today. Okay. How do I delete this? Oh, sorry. This is. Oh, I was doing annotate. Okay. Okay. Okay, so now we're going to be going over, okay, complex number arithmetic. So this is pretty straightforward. It's kind of like what we always do with real numbers. For addition and subtraction, you just add and subtract the the real and non-real parts separately. For example, we have A and C are the real parts, so we group those together into A plus C. And then we have B and D are the imaginary parts, so we group that together to B plus D. And multiplication is also pretty straightforward. We just expand, and you see that this is what we get. And note here that we have a BDI squared, and since I squared is just, oops, okay, that kind of blocks it, but I squared is equal to -1, so that's why we have a minus BD here. And that's why it's that then it becomes real, so that's why we have AC minus BD there. Okay, so here are a few example problems you guys can work on. Um, I'll probably give like 5 minutes, and if you solve it, you can directly message me, and then I can tell you if they're right or not. Okay, so 5 minutes is up. Okay, and I guess we can, does anybody want to go over the solutions to these questions? Okay, I think I'll just go over them. So, so we noticed that if we just constrain z to be a real number, then the first question would have no solutions. However, since we can use what we just learned about imaginary numbers, so oh, okay, wait, hang on. All right, okay, so we can use what we just learned about imaginary numbers. So for one, we can say that z squared z squared is equal to negative 20 25, and z is equal to square root of negative 20 25. And so that means that z is equal to plus or minus 45i. Okay, does anyone have any questions here? Okay, so for two, so 2026 is a really big number, and we can try seeing if there's a pattern for powers of I. So listing a few small powers out, we see that I to the first power is just I squared is equal to negative 1 from the definition of I, and then I cubed is equal to negative I, and then I to the fourth is equal to 1, and I to the fifth is equal to I again. So we see that there's like the cycle repeats every four powers. And so if we divide the exponent by four, and then we can find the remainder to see which power it corresponds to here. So 2026. So 26 is equal to 2 mod 4. So 2026 is also equivalent to 2 mod 4. Mod 4. So then we can see that it just corresponds to I squared. So the answer is equal to negative 1. So negative 1. Does anyone have any questions here? Okay, so moving on to number 3. To question 3. Find all values of k such that this is a real number. So we can expand this product. So 3 plus 2i times 3 plus ki. So expanding this, we get 9 plus 3ki plus 6i. And then plus, okay, my pen is plus 2ki squared. And then, so we can simplify this. So 9 plus, okay, it's a really bad. This is 9 plus 3k plus 6i. And then we see that I squared is just negative 1, so this is minus 2k. And then for this to be real, we want okay, well, I guess we can also just group it here. So 9 minus 2k plus 3k plus 6i. So as we saw in like the previous slide, if we want this complex number to be real, then the coefficient of the imaginary part has to be 0. So that means that 3k plus 6 is going to have to be equal to 0. So k is going to be equal to negative 2. So that's the answer for this one. Does anyone have any questions? Okay. Okay, so now we can talk about conjugates. So if C is equal to A plus BI, then A minus BI is called a conjugate of Z, and it's denoted as Z bar. And a non-real number and its conjugate are referred to as a conjugate pair. And so these are some like, oh, okay. And so these three are some, these things are some important properties of conjugates. So Z times its conjugate is always a real number, and we can see why by, so if let Z equals A plus BI, and then its conjugate will be A minus BI. And then if we expand this, we get A squared minus ABI plus ABI minus B squared times I squared, B squared I squared. And if we simplify this, we have A squared minus B squared I squared, and then I squared is equal to -1, so this is just A squared plus B squared. And since A and B are real, then that means that A squared plus B squared is also real. So yeah, this is a pretty important property, and it's good to like know this. Okay, now we can also prove these two properties, and these are also pretty straightforward. So if we let Z is equal to A plus BI, and then W equals C plus DI, then the conjugate of C plus W is going to be equal to the conjugate of A plus BI plus C plus DI. Um, so then this is going to be equal to the conjugate of, so combining the real parts, and plus B plus DI. And this is just going to be equal to A plus C minus, oh, okay, we can put a parenthesis around the real parts too, minus B plus D I. So this is the conjugate of Z plus W. And now if we do it separately, like in the left-hand side, then we have, on the right-hand side, then we do it separately. So A plus, the conjugate of A plus BI plus the conjugate of C plus DI. And then this is equal to A minus BI plus C minus DI. And then we combine the real and non-real parts. So A plus C minus B plus D I. Okay. B plus D I. Okay, and we see that these two are the same, so that's why the second property is true. And we can, I guess, also do something similar for the for the last one. So again, if C is equal to A plus BI and W is equal to C plus DI, then we have that A plus BI times C plus DI is equal to the conjugate of AC minus BD plus AD plus BC I. And then this is equal to AC minus BD minus AD plus BC I. So that's the if we do it together, and if we do it separately, we have A minus BI conjugate of, okay, sorry, conjugate of A plus BI times the conjugate of times the con oh okay times the conjugate of C plus DI, and this is equal to just A minus BI times C minus DI. And again, we see that this is going to be equal to AC minus BD minus AD plus BCI. So we see that these two are also equal, so this third property is true. And for this last one, we can show this by letting z is equal to a plus bi again. So for the first one, the real part of z is equal to z plus conjugate of z over 2. So I don't think I talked about this, but so when we have, so z is equal to this, so I said that a is the real part and okay, a is the real part and it can also be denoted as this, and can also, b can also be denoted as this. Yeah, so if we plug in a plus bi for z here and a minus bi for the conjugate of z, and we divide it by 2, we get 2a over 2, which is indeed a. And if we do the same here, a plus bi minus a, and then subtracting a negative is positive, so a plus bi over 2i, we get 2bi over 2i, which is indeed also b. So that's how we can prove this last one. Does anyone have any questions here? Okay. So moving on to the next. So here are some problems you guys can try. So you might have noticed that when we talked about complex number arithmetic, we didn't cover division, and this is because you need like you need to use conjugate properties to do this. And so to solve these problems, try and like use like some of these properties to solve them. And again, if you have any questions or if you have solutions, just private message me. Okay, so I think we can go over the solutions now. Does anyone want to share their solutions? Okay, if not, I'll just go over it. So we want to write uh we want to write this expression as a plus bi, and it might be like hard to see what to do with this because there's like another complex number in the denominator. But if we look back to one of the properties on our previous slide, for example, this property z times the conjugate of z is a real number, we can use that to simplify this expression. So if we multiply the conjugate of 3 minus 2i on both the numerator and denominator, we can make the denominator real, and that will make the simplification easier. So if we do, oh shoot, sorry. Okay, so if we do that here, so we do 2 minus I over 3 plus 2i is equal to 2. Okay, this is, okay, so we have 2 minus I over 3 plus 2i is equal to 2 minus I times the conjugate of 3 plus 2i, which is 3 minus 2i, over 3 plus 2i times 3 minus 2i. Then we can simplify this and the denominator will be real. So we get this is equal to, the numerator is equal to 6 minus 4i minus 3i, and then plus 2i squared. So this is minus 2. And then the denominator is 9 plus 4i. 9 plus 4. So then this is just equal to 4 minus 7i over 13. So we can write this as this. Okay. So this is how you can divide two complex numbers. You multiply by the conjugate of the denominator, and that'll make the denominator real, and that'll make simplification much easier. Okay, so does anyone have any questions? Okay, so now we'll move on to this question. This question's a little bit more complex, but it uses basically the same principle. So we can multiply both sides by 2z plus 3 just to like get rid of the fraction and to make this like nicer to work with. So 3z minus 5i is equal to 3 minus 2i times 2z minus 3. And then we can expand this right-hand side, so we get 6z minus 9 minus 4z, 4iz plus 6i. Sorry, this is a plus 3. I don't know why I wrote minus 3 here. So plus, minus. Okay, so this is minus 6i. And then we want to solve for z, so that means that, so we want to isolate it first. So we can get that, so negative 9 plus I is equal to 3z minus 4ic is c times 3 minus 4i. So now we have z is equal to negative 9 plus I over 3 minus 4i. And this is basically just what, like, complex number division. So we can do the same thing we did for the last problem to simplify z. And so z is equal to negative 9 plus I times the conjugate of the denominator, so 3 plus 4i over 3 minus 4i times its conjugate, 3 plus 4i. And then we see that the numerator simplifies to negative 27 negative 27 plus minus 4, so negative 31, and then minus 33i. Oh, no. So minus 33i divided by, this is 3 squared plus 16, so it's 25. So this is our answer. You could also, yes, to this. Okay, so this is what z can be. All right, does anyone have any questions here? Okay, so we'll move on to the next section now. Oops. Okay. So now we're going to be talking about the complex plane. And so the complex plane is basically like a Cartesian plane, but there's a real axis here and an imaginary axis here. So for example, if we were to say c is equal to like 1 plus 2i, then to graph, okay, that's a really bad eye. Okay, to graph this, okay, if we do tick marks. So the real part is 1, so we do this. So it's going to be along this line. And then the imaginary part is 2, so it's going to be along this line. So that means it's going to be here. And then if we were to do like, for example, 3 minus 4i, then we have this is 3, and then it goes 4 along, negative 4 along the imaginary axis, so it'd be down here. So it's basically just like graphing points on a Cartesian plane. It's just that there's an imaginary and a real axis instead. And some properties that I guess we could say about this is that, so if we were to have z is equal to here, then negative z would be, if z is 1 plus 2i, negative z is negative 1 minus 2i, so it would be here. And we see that it's just like 180-degree rotation around the origin. And okay, I'll label this c, and then this is negative c. Okay, and then if we have z conjugate, the conjugate of c, then we see that would be, so 1 minus 2i, so that would be here. This is z hat, oh, sorry, z bar. And that means that the point z and z conjugate are reflections over the real axis. And if we have, then we also notice that negative z and c conjugate of c are reflections over the imaginary axis. So these are like pretty obvious, but I guess it's good to know. Okay, so now we're going to talk about magnitude. So the magnitude of c, which I guess you could use, I guess people usually use like the absolute value symbol to denote this, is this distance from z to the origin of the plane. So similar to like a Cartesian plane, the origin is, oh, what did I do again? The Cartesian, similar to the Cartesian plane, the origin is here at 0, 0. So z is the distance from basically, it's just the distance from the origin. Okay, using our previous example again, so 1 plus 2i, then the distance is just the length of this. And then we see that this is pretty easy to solve because it just uses Pythagorean, right? So, oh my God, that's a really bad line. Okay, so we can just do this. We see that this distance is just the distance along here squared plus the distance along here squared, and then we take the square root. Um, and basically that's just the formula. So this is based on the Pythagorean theorem. And another property that we see is true is that z times the conjugate of z is the absolute value of z squared. I think we probably already used this in the last problem. It's just pretty straightforward. Times a minus c is equal to a squared minus abi plus abi, and then minus b squared I squared. And then negative ABI and ABI cancel out, so we just have a squared minus b squared I squared, and then I squared is -1, so this is just a squared plus b squared. And then we see that this is just the square of square root of a squared plus b squared. So that's why this is true. And this is also pretty useful. Yeah, okay. So now we can move on to the next slide. Okay, so I guess have 3 minutes to try this problem. And if you solve it, you can message me with the solution. And if you have any questions, you can also private message me as well. Okay, so I think we can go over it now. Does anyone want to present their solution? Okay, I'll go over it now then. So I worded this problem kind of badly because I know it says find the complex number, but there are two solutions to this problem, so that's my bad. But yeah, so to this problem, so like a pretty good way to do these is letting c equals to a plus bi. And then we can use this if anyone remembers the this property down here, real part of c is equal to c plus conjugate z over 2, we can use that to solve this problem here. So because we're given that z plus conjugate of z is equal to 6, um, that means we know that 2a, okay, we know that 2a, we know that 2a is equal to 6, so that means that a is equal to 3. And then we're given that the magnitude of z is equal to 5. So we have, and from the formula, we know that the magnitude of z is equal to square root of a squared plus b squared. And then we know that 5 is equal to the square root of plugging a equals 3 in, so 9 plus b squared. So 25 is equal to 9 plus b squared. So b squared is equal to 16. And here we have to be careful because b can be plus or minus 4. So there's two complex numbers z that satisfy this. So one is z is equal to 3 plus 4i, and the other is z is equal to 3 minus 4i. And you might notice that these are conjugates because they're symmetric. Okay, does anyone have any questions? Okay, so now we can go into our complex roots part of the lesson. Okay, so this is a review from like probably Algebra 2. So these are, I guess just a review. So the fundamental theorem of algebra states that every non-constant one-variable polynomial with complex coefficients has at least one complex root, and every polynomial of degree n has exactly n complex roots. And the factor theorem states that every complex number a, the binomial a x minus a is a factor of the polynomial f of a if and only if f of a is equal to 0. And the rational root theorem states that if p over q is a rational root of f of a is equal to a of n, an times x to the n plus an minus 1 times x to the n minus 1 plus dot 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 plus a1x plus a0, where p, q, and all of ai are integers, and GCD and the greatest common divisor of p and q is equal to 1, then a of 0 is a multiple of p and a of n is a multiple of q. So this is just, I think this is like a prerequisite, and it should be covered in algebra too. Yeah, and so complex roots, okay, complex roots are useful when like, because like not all polynomials have real roots. So for example, this is like when it's like pretty nice and all the roots are real, and it can be factored like this. However, this is not always the case. For example, we might have like a polynomial like this, where you can't factor it nicely. Um, but if we allow complex roots, then this can be solved. So yeah, we can factor as x x minus 2i times x plus 2i, and then the roots would be 2i and negative 2i, so it has imaginary roots. Does anyone have any questions? Okay, so here are two examples. So these two like might be a little tedious, but I think it's probably good practice the for the theorems that I stated before. Okay, sorry, I made a typo here. It's supposed to be X. Not 2017. Yeah. Okay, I'm gonna go over the solution now. Okay, so these are kind of tedious, but yeah. So first we can try and like simplify this to get like to factor out the real roots first, and then we can deal with the non-real roots. So using the rational root theorem, we can like test possible factors of the constant term and divide it by the factors of the leading coefficient too. So I guess if you test enough out, you'll get x is equal to, okay, wait, you get, you get, okay, for the first one, x is equal to negative 3 over 2, x is equal to negative 3 over 2 is a real root. And then if we do polynomial division, then we see that. So um, we have, so that means that 2x plus 3 is a factor of this polynomial. So if we do polynomial division, we can get like the quotient. So okay, I won't do the polynomial division out, but this is what we get. And then we can solve this part. So set this part equal to 0. Then using the quadratic formula, x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So it's just like this. And then this is negative 1 plus or minus root negative 23 and all over 2. So we notice that this part we can write it as like in terms of I, so negative 1 plus or minus I root 23 over 2. So here are our other two roots. So our roots are x is equal to negative 3 over 2, negative 1 plus, okay, I'll write it up here. So x is equal to negative 3 over 2 and negative 1 plus I root 23 over 2, and then negative 1 minus I root 23 over 2. Okay, so these are our three roots. Okay, so, okay, now for the second problem. Oh, does anyone have any questions about this one? Okay, so for the next question, we can just do something. Okay, next question, we can do something similar. Um, so first we can find the real roots and then use that, and then simplify the polynomial to find the non-real roots. So we can test factors of 36 to use the rational root theorem, and then we get that x is equal to 3 and x is equal to negative 4 are the real roots of this equation. And okay, someone has an answer. Okay. Okay, so these two are the non-real roots, and then that means that um x minus 3 and then and x plus 4 is a factor of this polynomial, and we can expand this to get x squared plus x minus 12, and to get the quotient we can use polynomial division again, and then from that we get that the leftover polynomial is 2x squared minus 2x plus 3. Okay, and I'll write the full thing out times x plus x squared plus x minus 12 is equal to 2x to the fourth minus 23x squared plus 27x minus 36. And we want to set this part equal to 0, so 2x squared minus 2x plus 3 is equal to 0. And then again, we can use the quadratic formula to get x is equal to negative b plus or minus the square root of b squared minus 4ac, so 4 times 6, all over 2a is 4. And then this is 2 plus or minus root negative 20 over 4. What's it sideways now? And then we have this is 1 plus or minus I root 5 over 2. So these are the other two solutions. Um, I'll write down the four solutions here. And you may have noticed something interesting about the roots of these two polynomials. When we have, it seems that when we have complex roots that they come in conjugate pairs. For example, here we have like just these two roots are conjugate pairs and these two roots are conjugate pairs. And there's actually a property that, I'll move on to the next slide for this. There's actually a, there's actually a property that if p of x is a polynomial with real coefficients, if z is a root of p of x, then conjugate of z is also a root of x. And so the non-real roots of p of x come in conjugate pairs. So a really important part of this like statement is that p is a polynomial with real coefficients. So this is not necessarily true if p has non-real coefficients. And then you'll see why when we prove this. So, okay, so now we can prove this. So we have p of x, we can write it as a of n times x to the n plus a of n minus 1 times x to the x x to the n minus 1 plus a of n minus 2 x to the n minus 2, and then all the way to a of 1 x to the 1 plus a of 0. And we see that, and then if c is a root of this, we can just see that a of n times c to the n plus a of n minus 1 times c to the n minus 1 plus dot 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 a of 1 times c plus a of 0. They should be equal to 0. And then now something we can do is we can take the conjugate of both sides of this equation. So we have conjugate of a of n c to the n plus a of n minus 1 times c to the n minus 1 plus a of 1c plus, I should put a plus here, plus a of 0 is equal to 0 conjugate. And the conjugate of 0 is just 0. And if you remember one of the properties we talked about earlier, where we have like CW is equal to Z times the conjugate of W. So we can use that here. Oh, and we need to use this first. We need to use Z plus W is equal to the conjugate of Z plus the conjugate of W. So we can use this first to separate the conjugates here. So we have this as A of n, C of n, plus conjugate of A of n minus 1, C of n minus 1, plus conjugate of A of n minus, okay, dot, 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 plus conjugate of A of 1z, plus conjugate of A of 0 is equal to 0 because, as we said earlier, conjugate of a real number is just itself. All right. And then now we can use this property here that you can separate it. So A of n A of n, this is equal to a conjugate of A of n times conjugate of z to the n plus conjugate of a to the n minus 1 times conjugate of z to the n minus 1 plus conjugate of a to the 1 times conjugate of z plus conjugate of a to the 0 is equal to 0. And then now we can use the fact that the conjugate of a real number is just itself. And so we can simplify this even more by just like removing the conjugates from the real parts. So z to the n. is equal to 0. Okay, so this looks pretty similar to our equation here now. So now we can use this fact again because we see that um, this means that z to the n, this means that, okay, so that means that z to the n is equal to z to the n. So you can see that this is just an extension of this because if you just apply it multiple times where z is equal to w, that's what we get. So that means we can move the that means that we can move um the conjugate inside of the power. So a of n times conjugate of z to the n plus a of n minus 1 times conjugate of z to the n minus 1 plus etc. 1 times conjugate of z plus a of 0 is equal to 0 is equal to 0. Okay, so that means we see that this is just equal to this, but we replace z with conjugate of z, and it's still equal to 0. So that means that if z is a root of this polynomial, so is conjugate of z. So that's like a proof for this theorem, and it's like very useful for solving like algebra problems. Does anyone have any questions on this? Okay, I think that's it for today, and here's the homework. It's from the Precalculus Enhanced book, and the homework is 2 to 40 evens on page 233. And if you have trouble doing the homework or if you have any questions, if you have any questions, you can ask now. And if you have any questions, further questions or questions on the homework, you can come to office hours on Wednesday or Saturday. Or you can ask next class too. Okay, I guess see you guys on Thursday or Wednesday then.